Thank you very much. So my name is Amine, and I'm going to talk about affordances. But first, some background. I am interested in swarm robotics. I'm interested in learning collective behaviors with many, many small, tiny robots that are simple with limited capabilities. And for that, I'm using a framework that is a special framework in evolutionary robotics, which is embodied evolutionary robotics, where the evolution is decentralized and it's embedded inside the agents themselves. It is on board, it is online, because the agents are executing their task while they're learning it. And this is kind of interesting because it enables us to have different behaviors. Different agents can have different behaviors. However, it has many challenges, and some of them are due to the dynamics of the systems, where we have agent interact with other agents, agent interacting with their environment. So this induces a lot of complex dynamics. To start, I'm just going to review a little bit these algorithms. They're simple algorithms. So as I said, the evolution is embedded inside the agents. So every agent executes a algorithm like that. That algorithm alternates between two phases, a behavioral phase and then an evolution phase. During the behavior phase, the agent moves around, execute their genomes, their controllers, and whenever they meet, when two genomes get close to each other, they broadcast their genome. That's how they share the genetic information. So, and then they collected it and they store it for the next generation. And that's how we do, this is how it happens. And at the end of the behavioral phase, once some few time steps have passed, every genome then look at all the genes that he collected during the previous behavior phase. And he will then select a new genome with some selection method, and then mutates it and replace its own genome with that new genome. If an agent doesn't collect anything, he becomes inactive until he gets new genetic material from agents passing by. Okay, but he stays inactive. Okay. So these algorithms have different dynamics, they have complex dynamics, I mean, interesting dynamics, let's say too complex, and they can be viewed or they can be compared to a selfish gene metaphor, in which we have a set of genes that are embodied into agents and they compete for survival. And they use their agents to spread. If a gene doesn't spread, it is lost. So there is an incentive to move and to evolve strategies that enables you to move and to spread your genes. However, there is also a pressure. There is this pressure from the environment that will hinder that. In a sense, if the environment is too difficult, there's too much obstacles, or there are too many agents, or there are too few agents to have meeting opportunities, then you don't survive. So the survival of the agents or the survival of the genes here is linked to evolving behaviors that are good at spreading and that are good at moving around physically. So in this context, today's questions, or what I'm trying to understand, is what are the things that make these algorithms emerge certain behaviors in open-ended environment. In open-ended environment where no selection there is. Okay, there's no task to solve or nothing to achieve, but just evolve. So to motivate this, I have to go back a few years ago when I was with a friend, Nicolas Bourdèche, who presented 10 years ago exactly here, not here, but in New York, in A-Life. He presented this interesting paper. It was a short paper. And I remember being in his office and he was showing me his his experiments and everything. And that's what he tried. Take a bunch of agents, just mobile agents, simple, the same algorithm that I presented, put them in an empty environment and give them and put some randomly positioned landmarks. These landmarks don't have any advantage, don't give any advantage to the agents. Just things the agents see or perceive. And then when the agent has to select a new genome at the evolution phase, he just picks a genome randomly. No strategy, nothing. Just pick one. Obviously, if you don't have anything, you die. Right, you are inactive. So what the result, and he left this running for different generations, and the result was this. These are trajectories at the end of the evolution. And what we see here is interesting behavior. We have these clusters. First, the clusters, we notice the clusters that represent agents orbiting around the landmarks. Okay, remember the landmarks don't provide anything. You're just things we see. We see those lines that kind of reminds us of Voronoi-Tellus tessellations. And we notice that the agents have learned to gather at specific spots and have learned to maximize their these spots kind of maximize their mating opportunities. There's a large supply of genomes at those spots because there are many agents. So all this, it was very interesting, but the most interesting thing is that it happened all the time. Every run gives you something that resembles this. So my question at that time was, how come? How it's weird. How does it come? And can we explain it? Can we have some kind of argument that can explain this? So this is an attempt to explain this. My attempt is just these agents or these kind of algorithms can tend to use the affordance of the environment. So I took inspiration from eco-psychology and particularly from the work of Edward Reed, where these are quotes from his book, where he says the affordances in the environment are things are selective, create selection pressure towards certain behaviors. Okay, and he also says that there are resources for obtaining value, mating opportunities, throughout the regulated actions, interaction with the environment. So my claim in here is that agents that we saw exploit those affordances. They use what the environment gave them. They also they use the landmarks in a certain way. They use the walls. They use the other agents. Anything that is perceivable to them is something that they use for the evolution. And this creates a certain pressure towards certain behaviors. That's what it happens all the time. There we go. So how can we verify this, and how can we explain it, and how to have some insight on this? So the thing is that we had to design something that has to prevent the fixation of behaviors. If we can avoid behaviors to converge to certain things, maybe we can see different things. So that's the essence of this experiment. Very, very simple experiment. So in this setting, I took the same setting as my friend, colleague. We took 1,000 agents. We put 10 randomly positioned landmarks. Remember, the landmarks don't provide any advantage. They're just here. And we evolve only the weights of the neurocontrols. The genomes is just the weights. And there is no predefined task. It's open-ended. So, and we have two variants. Since we are in open-ended, we have two variants. The first one is the random selection one, when agents pick up a random genome and then carry on. And the second one is the one that pushes for originality, which is novelty. The one that kind of like prevents the fixation of behaviors. And we use different measures to compare to measure in this experiment. And then I'm just going to present the results. First, just a quick note on promoting novelty. Okay, how do we do that in our setting, which is distributed online and everything? The quick answer would be, but just take any diversity algorithm, any QD algorithm, and use it. The caveat here is that we can't really do that because we don't have any archive. The population is distributed, the algorithm is distributed. We can't store anything. We didn't store history, and so we can't use an archive. Okay. The second thing, and the most important thing, is that the behavior is linked, tightly linked to the agent's experience in a specific moment. So a genome creates a behavior with the specific agent in a specific place physically and a specific moment in time. If we take the same genome somewhere else, it will probably exhibit another behavior. So comparing behaviors, as in traditional QD algorithms, becomes difficult. Okay, so we have just in this sense that we have to reconsider what is novelty. And whereas in traditional sense, novelty means seeking originality throughout the evolution, the whole course of evolution, we define the novelty toward seeking originality at a certain given time. That's what we can, that's all we can do. We don't have much. We don't have the history, we don't have the archives. So how do we do that? Well, at the selection step, the agents will select randomly, will select the behavior that is different, the most different behavior in the reservoir they have, in the list of genomes they have. I can explain this later, but I have to go. So let's look at the result. For the first thing, we look at the behaviors, the trajectories that are in. These are snapshots across the beginning, the middle, and the end of the evolution. And we see that both algorithms start having behaviors that are similar. But however, across time, we see that the random, the top line, the random changes behavior. It starts clustering, whereas the novelty variant starts to spread. And you have the rich behavior and the agents go everywhere. And then if we look, and this is interesting because it's also consistent throughout all instances. This happened every time. We did many, many runs, and this happened all the time. This beginning, middle, and end. If you look at some quantitative measures, agent, in both cases, in both instances, agent managed to evolve strategies that enables them to survive. This is the number of active agents, and we see that both instances managed to survive. There's no mass extensions, so that's a good thing. We see also that from the previous slide and from this slide, that the agent using novelty travels very much, cover a lot of time, and then we have to ask the question, can they manage to survive? Yes, they did. So they created strategies that managed to survive. If we look at the mating, how many mating encounters, how many transfers, how many inseminations they happened, we can see that the random instance has twice as much transfer, twice as much genome transfer as the novelty. But however, since they live in clusters, they transfer regularly to the same people, same agents. So if you look at the other curve on the left, we see that the novelty agents are twice as much efficient because they inseminate different agents. They're more efficient at spreading. Finally, if you look at the phylogeny, that's one of the tools I use to look at evolution of these things. We see that there are many, many niches that do not share much of the genome, the genetic history. These niches are there are more in a random case than in a novelty case, And this suggests that, and this needs to start early on in the evolution. So this suggests that those clusters that we saw start very early on in the evolution and then stays isolated throughout the evolution. To sum up, I can discuss different things later, but to sum up, my goal or our goal was to understand the dynamics that drive open-ended evolution in EER algorithms. This is a specific case. And my claim was that with nothing else in the process, the affordance that exist in the environment, the possibilities, if we can say, are the ones that induce the emergence or induces a specific pressure towards certain behaviors. We designed this experiment and we compared, and we saw that one experiment with only environmental pressure from the environment, and the second variant was a pressure for originality and the pressure from the environment, and both strategies managed to survive, so managed to evolve correctly, except that for the random case, the agent exploited or used the affordances, whereas in the novelty case, they didn't. Although they both started the same behaviors, with the same behavior, sorry. So since they started the same behaviors, one would say that maybe the behaviors that are exhibited by the random agents are easy behaviors that when we fall in, there are minimums. Local minimums, when we fall in those behaviors, when we're stuck in those behaviors, we don't move because there's no other incentive to move away, except if there's another incentive like a fitness or another pressure, maybe we can move away. But as it happens, those behaviors those are the behaviors that we always fall in. So the affordances, the behaviors that are favored by the affordances are the one that we fall in. And finally, there's one thing that seems to be interesting to me. That one thing is that next time in the future, I'm looking at the open-endedness in my case differently, because I will see where are the affordances that drive certain things. And more interestingly, I'm thinking about things that are, for example, can we engineer such affordances? Can we make environments that can do this, can give a nudge, for example, for evolution and do things more interestingly? All right, thank you very much.